Picture the most ordinary thing you do online. You type an address, press enter, and about 200 milliseconds later, a page is on your screen. It feels instant, atomic, like flipping a switch. It is not. In that sliver of time, your computer looked up a name, opened a connection across the planet, proved the other side was who it claimed to be, asked for a document, and got it back. All through machines and cables owned by companies you have never heard of. The reason this works, reliably, billions of times a second, is not luck. It's a piece of engineering called the network stack, and understanding it is the single best investment you can make if you build, run, or debug anything that touches a network. Good news. It's built from a handful of clean ideas. Let's map them. Start with the problem layering solves. Imagine building networked software with no shared structure. Every app would have to solve the same brutal problems from scratch. How to find the destination machine. How to survive a dropped packet. How to share one cable between many conversations. How to turn bytes into signals. Your chat app and your email client would reinvent all of it, incompatibly. The fix is the one engineers reach for everywhere. Separation of concerns. Slice the problem into horizontal layers, each with one job. Each layer trusts the layer below and offers a clean service to the layer above. And conceptually, each layer talks only to its peer, the matching layer on the other machine. That one decision is why the internet could grow without being redesigned. A new Wi-Fi standard swaps the bottom layer without the web noticing. A new app protocol appears on top without touching the wires. You will meet two models, and people waste a lot of breath arguing which is correct. They serve different purposes. The OSI model, 7 layers, is a teaching tool and a shared vocabulary. It gives us precise words, so when an engineer says, "That's a layer 3 problem," everyone knows they mean routing and addresses, not cables or web requests. The TCP/IP model is the one the actual internet runs on. It collapses those 7 into 4 practical layers: link, internet, transport, and application. It's messier and more honest because it describes what was really built. We'll use TCP/IP as our spine and borrow OSI's vocabulary when it helps. Notice the mapping. TCP/IP's single application layer absorbs OSI's top 3, and its link layer absorbs the bottom 2. Let's walk the stack top to bottom and collect the protocol names as we go, because those names are the table of contents for this whole series. The application layer is where the protocols you actually experience live. HTTP carries web pages. DNS turns names into addresses. DHCP hands a new device its settings. NTP keeps clocks in agreement. Email rides on SMTP, and file transfer has its own family. Each gets its own episode later. Below it, the transport layer turns best effort delivery into something an app can rely on, or deliberately stays out of the way. TCP gives ordered, reliable, connection-based delivery. Lose a piece, and TCP resends it. UDP does almost none of that. It's thin and fast and lets the app decide. This layer also gives us ports, so one machine can hold many conversations at once. Now the bottom 2. The internet layer is the heart of the whole design. Its job? Move a packet from any machine to any other machine across as many separate networks as it takes. This is the home of IP, which provides the addresses everything depends on, and ICMP, the diagnostics channel behind ping and traceroute. Everything on the internet ultimately rides on IP. The link layer is the ground floor, where bits actually move between 2 directly connected devices. Ethernet frames data for a cable. Wi-Fi does it over radio. ARP sits here as the bridge that finds your neighbor's hardware address. This layer is about one hop, getting data to the next device, not the whole journey. That's the map. Almost every article in this series picks one of these boxes and goes deep. So how does data actually travel through these layers? Through a beautifully simple trick called encapsulation. As your data moves down the stack, each layer wraps it in its own header, like putting a letter in an envelope, then that envelope in a bigger one. When your browser sends a request, the application layer produces the HTTP message. The transport layer wraps it in a TCP header to form a segment. The internet layer wraps that in an IP header to form a packet. The link layer wraps that in an Ethernet or Wi-Fi header to form a frame. Only then does it hit the wire. On the receiving machine, the exact reverse happens. Each layer strips off its own header and passes the rest up. The web server's HTTP code never sees an Ethernet header, and the Ethernet hardware never sees the HTTP request. That's layering doing its job. Quick vocabulary check, because this one trips everyone up. The unit at the transport layer is a segment, at the internet layer, a packet, at the link layer, a frame. People say packet loosely to mean any of them, and in casual conversation, that's fine. But when precision matters, these 3 words point to 3 specific layers. Segment, packet, frame. Keep them straight and half of networking suddenly reads more clearly. Two design principles run underneath everything, and they explain not just how the internet works, but why it won. The first is the end-to-end principle. Keep the network itself simple and dumb and put the intelligence at the edges, in the end hosts. The routers in the middle do one job well, forward packets, and leave reliability, encryption, and application logic to the two machines actually talking. This is why innovation happened so fast. Inventing the web, or streaming, or a new app didn't require permission from the network or an upgrade to the routers. You just built smart software at the edges and ran it over the same dumb, reliable core. The network never had to know what you invented. The second principle is the narrow waist, and it's best pictured as an hourglass. At the top, a huge and growing variety of applications. At the bottom, a huge and growing variety of link technologies, from fiber to Wi-Fi to 5G. And in the narrow middle, holding the two halves together, sits one protocol, IP. Everything runs over IP, and IP runs over everything. Because all applications agree to speak IP, and all physical networks agree to carry IP, the top and the bottom can each evolve wildly without ever coordinating with each other. The waist stays narrow and stable while both ends explode with variety. Hold on to these two ideas. Almost every change in the second half of this series, from quick to software-defined networking to zero trust, is really a renegotiation of where intelligence sits and what that waist guarantees. Let's tie it together by following one web request the whole way, naming the protocols as they appear. You type the address and press enter. First, your machine needs the server's IP address, because the name means nothing to the network. It sends a DNS query, usually over UDP, and gets an address back. And if your device only just joined the network, some quiet bootstrapping already happened. DHCP handed it an address, a gateway, and a DNS server, and ARP found the gateway's hardware address. Now your browser opens a TCP connection and sets up encryption on top. Then it sends the actual HTTP request. Give me the home page. That request is encapsulated down the stack, TCP segment, IP packet, frame, and sent to your gateway. From there, it hops router to router. Each router reads only the IP header, picks the next hop, swaps the frame, and forwards it. The server decapsulates the request layer by layer, builds a response, and the whole thing runs in reverse. The page renders. A fraction of a second, across machinery spanning the planet. Every step there is a layer and a protocol you now have a name for. So there's your map. The internet is not magic and not one monolithic thing. It's a stack of cooperating layers, each with one clear job, each wrapping the layer above in its own envelope and trusting the layer below. Application protocols you touch, transport for reliable or fast delivery. The internet layer moving packets anywhere, the link layer moving bits to the next device. Encapsulation carries data down and up. And two ideas, the end-to-end principle and the narrow waist of IP, explain why it all scaled to the planet. The one-liner. The network is layers all the way down. Every layer wraps the one above it, and everything in the middle runs over IP. Next time, we stop looking at the whole stack and drop to the very bottom. The link layer. How Ethernet frames data, how a switch learns where everyone is, how ARP finds your neighbor, and how Wi-Fi became the default first hop. Before a packet can cross the planet, it has to reach the device one cable away. See you there.